So welcome back to another video. This will be a bit of a chunkier video, and it's our introduction to trigonometry. It's a word you might have heard before, but we'll talk about what it is. So today's learning objective is to know the formula for Pythagoras' theorem. We've talked about this before. We in fact talked about the proof as well. The trigonometric ratios, which I'm not going to say those, those ones, and apply them to find angles and lengths in right-angled triangles, and where possible, general triangles in 2- and 3-dimensional figures. This part about this last part here is higher only, and know the exact values of the trigonometric functions we're going to talk about. So just a quick starter thing. What's Pythagoras' theorem? We've talked about this before, but it's if we have a right-angled triangle such as this, and if we label sides A, B, and C, the most important thing is that C is the hypotenuse. We have that a squared plus b squared is equal to c squared. We talked about the proof of this a few videos back, so if you want to see that, you just check that out. It was in I think lesson 71 or 72, something like that. So this is what Pythagoras' theorem says, and yeah, that's kind of that. The other thing that we want to talk about is now trigonometric ratios, and what we have is so as a quick introduction, actually, theta, that's just another way of saying an angle. So you know how, for example, with algebra, we tend to always say, well, not tend, but the convention is if you're thinking of an unknown variable, you usually go to say something like x, right? And that's just a bit of convention. But it's the same principle with theta and angles. So if you have an unknown angle, you tend to just go to theta, which is kind of, it looks like that. That's what it's called. So this side here, it's pronounced, it's said as theta. It's a Greek letter. Math loves Greek letters for some reason, I don't know. And kind of, as like, for example, if we said, sine theta, we're saying kind of this unknown theta, it could take a range of values, for example. So what we have is if we label this as theta, for example, if we're thinking about for a right angle triangle, we can actually find that the ratio of this length, b, divided by the hypotenuse c, is actually some sort of function of theta, and this is what we call the sine function. Sine of theta on your calculator, so you can put this on your calculator. There's a sine button. If you put sine of theta for a right angle triangle, that it will equal to b over c, or opposite over hypotenuse. So, or rather, opposite over hypotenuse. And our hypotenuse is this length here, and an opposite is kind of the opposite to the angle. So this is the length opposite. This is the side opposite to the angle, and we have this some sort of function which takes theta. We've talked about functions before. It takes the angle theta. Somehow it kind of changes in a certain way. It does something to it in order to give you the ratio of the opposite side of a right angle triangle to the hypotenuse. And that's something kind of I guess partly you just have to understand, I guess, and memorize even. And then we have, similarly, if how sine takes the angle here and turns it into a ratio of the opposite to the hypotenuse. In the same way, cos, or the cosine, so this is actually called it says sine, but it's actually called the sine function. So that's why we don't say sin theta, we say sine theta, because that's actually the full name. It's sine, the full name of the function is sine, but we just shorten it to sin. So it looks like sin, but it's actually, we say s sine. The other function is cosine, and we shorten this to cos, and we actually just say cos theta or cosine. You can say cos theta or cosine theta. So cos of theta. So again, these brackets are kind of optional. We've talked about them in the functions video about if we have brackets that it's not saying we're multiplying cos by theta, we're saying cos and taking the function of theta of that. So that's kind of remember f of x, for example. It's cos of theta, not cos times theta. So cos of theta is equal to adjacent over hypotenuse. And as you can guess, adjacent would be this length here for this theta, this adjacent over this hypotenuse. And again, like sine, cosine is a function which takes the angle theta, and somehow for a right angle triangle will give you the ratio of the adjacent side over the hypotenuse. And we finally have another function called tan of theta, and you might be able to guess what this is equal to. It's equal to opposite over adjacent I mean, so we've done kind of the pairs, we've done opposite and hypotenuse, adjacent hypotenuse, so we're left with doing opposite and adjacent. So again, tan somehow, sorry, the full name of this function is actually tangent. And there's a reason for that, which you'll learn at A level, I think. So if you're really keen on trying to understanding all this tan kind of cosine trigonometric functions, check out the A level video. If that's completely obviously beyond the GCSE scope, but if you're interested to see where this comes from, check those ones out instead. So this is saying tan takes tan is a function, or the full name is tangent, which takes some angle theta and turns it into a ratio of opposite over adjacent. And this kind of works for all values of theta. So that's quite, if you think about this, it's actually quite surprising almost that for no matter what the value of theta is, we somehow have a function which will give us the ratio of two sides of a right angled triangle. So it's not kind of a rudimentary thing to do if you think about it. It's actually quite the fact it works for kind of all values of theta, i.e. from 0 to 180, right? That's kind of surprising, at least to me. I mean, I wouldn't be able to work it out on my own, to be honest. There is kind of a complexity to this. It's not kind of a very simple function. It's actually quite a complicated function, and we know it's a complicated function because we've seen the graph of it. And if we remember the graph of, for example, sine, it was that wavy thing. So wavy as in look like this. So there is kind of a bit of complexity to this, but at GCSE you kind of need to know that these apply for right angle triangles only. So this is true for right angle triangles. And the way we kind of the I guess mnemonic that we use is SOHCAHTOA. Sine is equal to opposite over hypotenuse. Cos is equal to adjacent over hypotenuse, and tan is equal to opposite over adjacent. SOHCAHTOA. So I think, it's not over here anyways. Sorry. So SOHCAHTOA. Just if you're ever in doubt about kind of which trigonometric functions do what, SOHCAHTOA is the way you remember them. And we can use this principle in quite a few questions, and you can find the sine of an angle on your calculator. So you just go to your calculator and you can say if you want the sine of 45 degrees, you go sine 45. You type that in, hopefully you can see that, and just hit equals, and you've got a number that comes out. So it's quite useful, and we'll see in some of the worked examples how useful it is. So this is kind of one of the worked examples. We're given a diagram, and of course, as usual, it's not accurately drawn. So our question is to calculate the value of x and give your answer correct to 3 significant figures. So that's actually quite a key piece of information. In significant figures, not decimal places. So how are we going to do this? Well, we're asked to we're given an angle, we're given the hypotenuse, and we're given the opposite side. So if I run through my SOHCAHTOA, I can think sine is the one that satisfies those. Sine involves the 3 things of an opposite, a hypotenuse, and the angle. And if we remember, sine of theta is equal to opposite over adjacent. Not adjacent, hypotenuse. Excuse me. And in this case, if we know theta, if we put theta as 60, so we say sine of 60 is equal to opposite, which is x, divided by adjacent, which is 32. Not adjacent, hypotenuse. And if we rearrange this, we can say x is equal to sine 60, which is a number we can find right on our calculator, times by 32. So this gives us, using our calculator, sine 60 is root 3 over 2, and then we times that by 32, we're given 16 root 3. We're asked to calculate this to 3 significant figures, so this is 27.7 to 3 SF. 3 SF. And kind of that's all there is to a question like this. Ooh, and don't forget CAM that we need, because we know that these are in centimeters. So that's how we do a question like this. A bit of a harder one, and I'd say actually, so we have kind of 2 right angle triangles this time around, instead of just one. ABCD, so ABC is a triangle, ADC is a straight line with BD perpendicular to AC, And perpendicular, remember, that means that they meet at 90 degrees. At 90 degrees, if they meet at 90 degrees, you know you've got a 90-degree triangle. So, that's something good. AB is 7 centimeters, BC is 12 centimeters, and the angle BAD or BAD is 65. Calculate the length of AC. Give your answer correct to 3 significant figures. So in this case, we can't really calculate the length of AC directly because we don't have a right angle triangle, and our SOHCAHTOA stuff doesn't work there. So luckily, the question has actually really helped us out by splitting our diagram into 2 right angle triangles, such as this. And we also know that ABC is a triangle. Yeah, so I was going to say that maybe ABC is a right angle triangle, but it kind of looks like that from the diagram, but it's not mentioned anywhere in the kind of description. So when I see this question, right, and I know I need to find the length of AC, you can't find it directly, so that means you need to find the length AB and the length DC separately. Now, to find the length of AD, let's consider that one first. Let's label that X, so we can say let AD equal X, and we label that on the diagram. Now, if we need to find X, well, let's think about the 3 things we have. We have the hypotenuse, we have the angle, and the adjacent angle. So, running through our SOHCAHTOA, we see that cos satisfies this. Cos requires your angle. Cos of theta is adjacent over hypotenuse. So cos x is equal to adjacent, cos of x, cos of 65. This is the angle. Cos of 65 is equal to adjacent, which is x, over hypotenuse, which is 7. So x equals 7 cos 65. We can put the brackets there, but that's completely optional. The brackets. As long as you kind of remember that it's cos of, not cos times. Cos. You can't say cos times a number. You have to be cos of something times a number, right? So yeah, just put the brackets there if you want, or it just depends on your personal preference. I'm not going to actually evaluate this in full right now because we need to find DC, and it's more than likely that DC is not going to be a nice number. So if I round this now and then I add it to a rounded DC later, I might run into trouble. So you just leave this in its exact form right now because it's an intermediate at these steps. You don't round and kind of convert into significant figures in intermediate at these steps. You wait till right at the end. So let's leave it at that. Now we can say y here. Now, how do we find y? Okay, so we have the length y here, we have the length 12, but we don't have an angle, right? We know this is 65, but we don't know what this angle is, nor do we know what this angle is. So we can't kind of, use the fact that the angles in the triangle sum to 180 and kind of figure out one angle. I thought maybe initially that this might be a right angle by the looks of the diagram, but even if it looks like that on the diagram, it's not specified anywhere in the question. So let's not assume something like that. So, and to be honest, if this was a right angle, right, it'd be a really easy question because we just apply Pythagoras, and we have 2 sides, and we can just find the final side quite easily. So we can't somehow convince ourselves this is a right angle. So we need to somehow calculate the length of this side, and you can think, okay, well, you can kind of reverse engineer this a bit because you don't have an angle, and you can tell that there's no way to find an angle. So the only other way with a right angle triangle to find a side is Pythagoras, right? So if we could somehow find this side, well, that might be able to do the job, right? So, but we know we can find this side by kind of SOHCAHTOA, right? We found this side by the same logic we can find this side. So maybe if we label this side A. So we've got the opposite, the angle and the hypotenuse. So let's run through a SOHCAHTOA and think about which one satisfies that. So just pause the video, have a think about which of the SOHCAHTOA satisfies that. So the answer is sine. So we know sine of 65 is equal to opposite over hypotenuse, 7. So A is equal to 7 sine 65. Let's just leave it like this right now. And we also know from Pythagoras that a squared plus y squared is equal to 12 squared. So a squared plus y squared is equal to 12 squared because it's a right angle triangle. So y squared is equal to 12 squared minus a squared. which is equal to 12 squared minus 7 sine 65 all squared. So y is equal to the square root of 12 squared minus 7 sine 65 squared. And of course, it's not going to be plus or minus that because we know it has to be the positive value because y can't be, a negative number. And again, as I've said before, just with working through these steps, you should be comfortable with the algebra so that you can do this. You don't need to kind of evaluate this on your calculator or with a number. If you keep it in its exact form, you're less likely to make some sort of rounding mistake or even a copying mistake. Now we know the length AC is x plus y is equal to x plus y, which is equal to x is 7 cos 65 plus the square root of 12 squared minus 7 sine 65 squared. And now this way you only have to plug it into your calculator once. The rest is kind of you've done by hand, and you're less likely to make those copying issues and kind of the rounding issues. So this way, if you only plug into calculator once, I guess that's a better thing to do. So you do 7 cos 65. So when you get cos, you actually have to put the brackets in this case. I'm not sure if you can see that, but when you type this, try typing this into your calculator, and you can kind of follow along. Yes, plus square root of 12 squared minus, and this is 7 sine 65 all squared. So it's important to put the bracket outside the 7 of sine 65. So there's going to be kind of a double bracket at the end of the 65 and the sine. And then we get that, and then we get 13.1441858, and then da-da-da-da. And we did it to 3 significant figures, so if we round it, that becomes 13.1. And what is this in centimeters? Okay, 3s. Sorry, that's badly written 13.1, isn't it? 13.1 3SF centimeters, and that's kind of that done. So this is quite this was quite an involved question because we had to use kind of 2 SOHCAHTOAs and kind of a Pythagoras, and then add them up, and then kind of there's some square rooting here, so it can be a bit tricky. But the way to kind of approach these kinds of questions is, especially the more complex ones where it seems that you need to use SOHCAHTOA, is to break it down into right angle triangles. Even if this was in 3D, that requires I guess a bit of imagination, but at the end of the day, just you have to break it down into simple right angle triangles. So now let's move on to the second part of the learning objective, which is to, if we zoom in here, is to know the exact values of sine theta and cos theta for theta equals 0, 30, 45, 60, and 90, and know the exact values of tan for 30, 45, and 60, and 0. Okay. So if we kind of maybe create a table for these, so you could honestly just plug this into your calculator and you've kind of always got the answer to this, but I'll kind of give you the way you can figure this out, even if you didn't have a calculator for some reason, and perhaps, and also there's quite an easy way to memorize this, and I'll tell you that in a second, that as well. So first thing we'll do is let's create some sort of table. We'll do tan later. Let's do kind of a sine and cos one. So theta, and in fact we'll just start off with sine theta. We'll do cos theta in a second. So 0, we need 0, 30, 45, 60, and 90. And maybe if you remember the graph, you might kind of remember what at least a pattern might look like. But if you don't, kind of no problemo. Okay, let's actually start off with sine 45, which is actually the easiest one to do, I think. So we need a right angle triangle. If we draw, that's the first step in questions like this. And we have a right angle triangle, and we need kind of one of the angles to be 45. And because one of the angles is 45, the other angles will also be 45. Because it's kind of 19 minus 45, 180 minus 19 minus 45 is 45, because angles in a triangle sum to 180. And because of that, this side will equal this side. And since we're only interested in the ratio, we can kind of give the hypotenuse any length. So, and kind of give each side any length. It really doesn't matter. So, what we do for convenience sake is label one of these sides 1. So this is 1, this is 1 as well. By Pythagoras, 1 squared, this hypotenuse, a squared plus b squared equals c squared. This hypotenuse will be root of 1 squared plus 1 squared, which is root 2. And we know sine of 45 is equal to, sine is, remember, opposite over hypotenuse. So 1 divided by root 2. If we rationalize this, i.e. times top and bottom by root 2, we get root 2 over 2. So sine of 45 is root 2 over 2. So this is actually the easiest one to do because we have an isosceles triangle. Now let's think about sine 60. And when we have 60, what we can do actually is we create an equilateral triangle. I'm actually going to use the triangle tool on here. Okay, that's not nice. Okay, that's not a very good equilateral looking triangle. That's getting deleted. Okay, well, I guess I'll have to free draw one anyways. Okay, so I mean that's not. Oh, that's a pretty bad triangle. Okay, one more time. Third time's the charm, right? No, I'd say that's a pretty good equilateral triangle. So we have an equilateral triangle. And of course, because it's an equilateral triangle, each of the interior angles is 60. And if we kind of split this down in the middle with a line such as this, we'll create two right angled triangles. And instead of being 60, that will be 30 right now. So we can turn this into two 30s. I'll get a red pen out. So that's 30. And of course, on the left as well, it's 30 as well. So. And again, because we're only interested in the ratios, we can kind of give each side whatever value we want. So let's go with 1 for convenience sake. 1, 1, and 1. And this whole length is 1. And now, since we've done a perpendicular bisector, we've actually kind of divided this into half. So this becomes 0.5, right? And if we think about what sine 30 is, well, sine 30 is, sine 30 is opposite 0.5 divided by hypotenuse. So, remember, sine is opposite over hypotenuse, SOHCAHTOA. So 0.5 divided by 1, which is 0.5. So we can do sine 30 as 0.5. And if we think about what sine 60 is, well, we think 60 here. We can think about what this length is here as well. So we know that. So for sine 60, we need the length here, right? So we call that x, for example. And we can figure that out by Pythagoras because we've got these two other lengths. So we have x squared plus 0.5 squared is equal to 1. 1 squared, of course. X squared plus a quarter is equal to 1. So x squared is equal to 3/4. So x is equal to root 3 over 2. So this length here is root 3 over 2. So let's get rid of this x here and write root 3 over 2. Root 3 over 2. So sine 60 is opposite root 3 over 2 over hypotenuse divided by 1. So this is root 3 over 2. So 60 was root 3 over 2. And now we have a final one. Sorry, two actually left. 0 and 90. So sine 0, okay, well, if you think about kind of sine is the ratio of this opposite. Well, actually, let me draw another triangle to illustrate this. And I'm not actually going to label the value of sine itself this time. That is such a bad triangle. Sorry. Okay, so this is theta, right? Sine is the value of, say, x over y here, right? Sine theta is equal to x over y. And now let's think about, as sine gets smaller and smaller and smaller, right? If the angle closes, you can just think about the kind of this line, for example, this y just coming in. So it kind of goes like that as theta gets smaller, and like that, and so forth, right? And as x keeps getting smaller and smaller and smaller, right? So you can think about when it's 0, right? When sine theta is 0, that's just a flat line. So the opposite will be 0. So sine theta and sine of 0 is 0. And if you just take a second to imagine that sine 0 is, if you take this line, you keep making it smaller, 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 and then at 0, it's just going back on itself, right? So x will at that point be equal to 0, and 0 divided by whatever is going to be 0. So sine of 0 is 0. And if we think about what sine of 90 is then, Well, we then got kind of this line, but it's going the other way. It's getting bigger and bigger and bigger and bigger until kind of, you know, until eventually, if you think about it, the only way we can get theta as equaling 90 is, you know, if this line is up here, right, and there's a 90 degree here and a 90 degree here, so if we draw, sorry, you know, this is sine 90, it looks like this, right? But we can't, you know, that wouldn't really look like a triangle, right? Because we'd have effectively this line turning into this line here. So we're effectively going, you know, let me delete this line actually. If we're rotating this line such that, you know, sine theta becomes 90. And that's not really a triangle, right? Because, well, this is 90 degrees, so it has to be that. So really we just eventually kind of, if you think about it, just get a line that's on top of each other. And so x is equal to y. So sine of, you know, and if x is equal to y and we divide them by each other, we get 1. So sine of 90 is 1. And if you don't believe me, you can check all of these on your calculator, by the way. So, you know, don't take my word for it. 0 and 1. And now we've kind of done the signs. And the way I remember this is, you know, you have root 0 over 2, then root 1 over 2, then root 2 over 2, then root 3 over 2, and then root 4 over 2. And so, of course, root 0 is 0, so 0 over 2 is just 0. Root 1 over 2, root 1 is 1, so that's just a half. Root 2 over 2, root 3 over 2, and root 4 is 2, so root 4 over 2 is just 1. So for sine, you can just think, you know, root 0 over 2, root 1 over 2, root 2 over 2, root 3 over 2, root 4 over 2. And it goes from, you know, it goes 0, 30, 45, 60, 90. So you can think of it going in intervals of 30 and 45 being in the middle because, you know, it's an interesting one and it's half from 90. Now let's think of cos of theta. It's literally the same principles as we did before. Let's think of cos 45 first. Well, cos 45, well, we think about, in this example, you know, cos 45 is equal to adjacent over hypotenuse. Remember, that's the soft toa. So adjacent is 1 and hypotenuse is 1 over root 2. So cos 45 is 1 over root 2, which is again root 2 over 2. So actually cos and sine of the cos 45 and sine 45 are the same. So it's root 2 over 2. Let's think about cos 30. So cos 30 in this case, if we look at this triangle here, cos 30 is adjacent over hypotenuse, so root 3 over 2 divided by 1, which is just root 3 over 2. And by that same like intuition, cos 60 is, if we look at cos 60, that's 0.5 over 1. So we have that as 0.5, we have this as root 3 over 2. And you can see kind of it's almost flipped, right? And if we actually kind of, the same intuition means as we did before about kind of the angles getting bigger and smaller, we get 1 and 0. So it's almost kind of, you know, it's, guys, I guess it's kind of, if we look at sine and we kind of flip it, I guess, or reflect it around this 45 one, you know, the 0.5 comes here, there's root 3 over 2 comes here, and kind of that kind of logic, that's what we get for cos. And so, as you know, sine is root 0, 1, 2, 3 over, yeah, and then this is actually, you know, the opposite, root 4 over 2, root 3 over 2, root 2 over 2, root 1 over 2, root 0 over 2. So that's how you think about cos. Tan, we can do the tan, so we don't actually, you know, if you remember the video on tan and kind of tan 0 and tan 90, you know, you'll see why the question doesn't ask you, so the learning objective doesn't tell you for cos 90. Tan 0 is just 0. And theta. And again, if we go back to our thing here, right, tan 0 is, you know, tan is opposite over adjacent, right? Sorry, opposite over adjacent, right? So opposite over adjacent. And if we think about if this angle, for example, becomes 0, well, this opposite becomes 0. So we think about adjacent as kind of, so that 0, it doesn't matter what this length here is, so the whole thing is 0, so tan 0 is 0. If we go to our 30, so tan 30 is, tan is opposite, is 0.5. The opposite is 0.5, divided by adjacent, which is root 3 over 2, times top and bottom by root 2, which is 1 over root 3, which is root 3 over 3. If we kind of rationalize that. So tan 30 is root 3 over 3. Tan 45, if we look at tan 45, that's going to be opposite over adjacent, which is 1 over 1, which is 1. Tan 60, we go to this angle here. Tan 60 is opposite over adjacent. Sorry, did I do that the wrong way around? Yeah. No, sorry. Tan 60 is equal to opposite root 3 over 2 divided by adjacent divided by 0.5, which just becomes root 3. And kind of tan 90 is kind of, I guess, undefined. If you go back to our video on what the tan graph looks like, you'll see why we don't tell you to specify value for tan 90. So this is kind of the exact values that you need to know. I've gone through how you can use kind of first off a right angle triangle with 45 degrees to think about the 45 degrees one, and an equilateral triangle to think about 30 and 60 if we divide that equilateral triangle into two right angle triangles, and 0 and 90 we just kind of think about, I guess, extreme cases. And there's a quick trick I talked to you about, like, root 0 and kind of ascending that way and descending for cos. And for tan, to be honest, I don't really know the trick. I guess, I don't know, I guess you could maybe think of your own way to memorize it. I don't know. I don't know how I used to remember tan. I think because there's only two values that you really need to remember. You can remember tan 45 as one, which is kind of an easy value to remember, but tan 30 is equal to root 3 over 3. I mean, you can think about if tan 30 is if you just remember the numbers root 3 over 3 and root 3, and you think about tan is kind of increasing in theta. So as theta increases, tan increases, and so root 3 must be going to 60 because kind of 60 is greater than 30 and root 3 is greater than root 3 over 3. So that might be a way you want to remember it, for example. So yeah, and tan 0, 0, I guess, that's, I guess, easy enough to remember, right? But these are exact values I think you ought to memorize. Sometimes, if you're not allowed a calculator or kind of in situations where you need these exact values, and more often than not, actually, what it is that you need to be able to recognize them, recognize these numbers rather than kind of being asked to convert it. That's where it comes off quite useful. So you might see a triangle with root 2 over 2 and you think, oh, that's such an ugly number. But if you know that kind of, for example, if you're given with a triangle such as this, right? If we have a triangle with, say, this is root 2 and this is 1 and this is 1, right? And you actually calculate the value of theta here and you think, how am I going to do that? But if you remember that, say, sine 45 is root 2, you can think sine of 45 is root 2, and that's 1 over root 2, right? Sorry, yeah, is equal to, if sine 45 is root 2 over 2, if you remember that, you can kind of recognize that the ratio of, say, here opposite over adjacent is equal to 1 over root 2, and you think, oh, that's sine 35. So that's kind of where it is more useful if you remember I guess, if you're spotting them. So that's where it's quite important to remember these. So moral of the story is do actually end up memorizing them. So yeah, hopefully that all made sense. This was kind of an introduction to trigonometric functions, which is a fairly difficult topic, so make sure you do practice some questions on this. And I'll see you guys in the next video.